Welcome back to another SolidWorks tutorial. Today we're going to perform a structural analysis of a stair with weldments using SolidWorks Simulation. If you're new here, don't forget to comment, like, and subscribe for more engineering content. Let's get started. As usual, we will start by creating a new study. Right-click on Simulation, then New Study. Static is selected by default, so just click on OK. Okay, now we need to set up our simulation environment. In the first step, we need to define the material properties. We'll be using AISI 304. We will do that by right-clicking on the part, then click on Apply Materials to all bodies. Just type 304 and select this one. Click on Apply, then Close. Okay, now that the material is applied to our part, we need to move on to the next step, which is defining shell elements on surface parts with 4 mm thickness, respecting the position of its faces offset option, and we should note that parts C are with 5 mm thickness. Let's go back to our model. Shell elements are used when working with thin-walled structures, such as sheet metal parts, plates, or surfaces. Instead of modeling the entire volume, shell elements reduce computational load by only considering the mid-surface of the part with an assigned thickness. This approach ensures that the model runs faster compared to solid elements. To do that, just click on the surface so that it gets highlighted in the simulation tree. Then right-click on it and select Define Shell by selected faces. Now let's select all the faces that we need to define them as shells. And let's set the thickness to 4 mm. And make sure to check this box, because you can see in the preview here, the bottom face of the shell is on orange and the top face is in green, while it's the opposite case in here. This is the top face and this is the bottom face. So make sure to click shell top and bottom. Then click on OK. Now we should do the same steps for the other surfaces. Right-click and define shell by selected faces. Select the faces. And let's set the thickness to 4 mm. Here we don't have to check the flip shell top and bottom box because it's already correct in the preview. So just click on OK. Great. Now we need to define the shell elements of these two surfaces. So just click on this surface, right-click on the simulation tree, click on Define Shell by selected faces, select this face and this one, set the thickness to 5 mm and check this box. Then click on OK. Now for the next question, it says immovable fixtures on joints A, which are these ones. Let's go back to our model. Right-click on Fixtures and select Fix Geometry. Then click on Joint. Let's go and check the joint A, which are these ones. Then click on OK. Now for the next question, we need to set a force of 900 Newton on B. To do that, let's go back to our model, right-click on External Load, and select Force. Make sure to select Joint We can zoom in and select this joint. Now we should select the direction of the force. We will select the top plane. Scroll down a bit. The force should be normal to the plane, so just click on here and set the value to 900. And you can see in the preview that the force is in the opposite direction that we want. So we need to flip it by checking this box, reverse direction, then click on OK. Okay, now that the setup is complete, let's run our simulation. Click on Simulation and run this study. Thickness is not defined for one or more cells. It's okay to see errors sometimes. And click on Cell Manager. You will see that this surface have a thickness 0 millimeter. We didn't set the thickness for this part, so we can just do that right here. Let's set it to 4. Then click on OK. Now we can run our simulation. Okay, so this is our result. Now let's go back to the questions. What is the maximum axial stress of beams with 3 decimal places? We can answer that by right-clicking on result, then click on List Beam Forces. Here we can see that we can select forces or stresses. So we will check the stresses, then click on OK. Here we can see the axial stresses. Here we can check this box to show extreme values only. And that's it. Let's move on to the next question. What is the maximum stress in megapascals on the part highlighted with the letter D? Okay, you can answer that by right-click on stress, then select probe. Now choose on selected entity and select this surface. Click on update, and here we'll see the results, and the maximum stress is 4.512 Newton per millimeter square, which is megapascal. And that's it. This wraps up our tutorial. I hope you found it helpful. If you did, don't forget to comment, like, and subscribe. See you on the next one.